Welcome to Algorush. Have you ever stopped to think about how a massive system finds one tiny piece of information among billions and does it in the blink of an eye? Well, today we're going to pull back the curtain on the ingenious engineering that transforms all that digital chaos into perfect, lightning-fast order. So let's just start with this question right here, because it's at the heart of almost everything we do online. I mean, searching for a photo, booking a flight, loading a web page, we just expect it to be instantaneous. We take this speed for granted. But how is that even possible? To get our heads around that, we have to start at the very bottom. A storage device, an SSD or an old spinning disk, is fundamentally just a gigantic, unstructured line of bytes. It's a mess. If you don't have a system, finding anything would mean scanning the whole thing from beginning to end. It is pure, absolute chaos. So, that's our challenge, right? The entire game is about imposing a clever structure on top of this chaos. We need to build a kind of blueprint that lets us navigate this sea of bytes with incredible precision and speed. Now, you might be thinking, well, why not just dump everything into a simple text file? That's what we call the simple flat file approach. And yeah, it seems easy. But if you want to find a single record, you're stuck reading the entire file. And what if you want to change just one little thing? You might have to rewrite the whole file from scratch. It's just wildly inefficient. And that's exactly why we use these specialized formats built for fast lookups and quick in-place updates. These specialized formats, they basically play by three brilliant rules. First, be efficient with your storage. Don't waste space. Second, and this is our focus today, be efficient with access. Find what you're looking for in the absolute minimum number of steps. And finally, be efficient with updates. When something changes, you want to touch the disk as little as possible. So where do we begin building this structure? Well, the very first layer, the foundation of it all, starts with a simple but really powerful concept that works directly with the hardware, the page. Instead of thinking about individual bytes, which would be like trying to move a beach one grain of sand at a time, the system uses buckets. These buckets are our pages. They're fixed-size containers for our data, and all the reading and writing to the disk happens in these page-sized chunks. It's just way, way more efficient because it's how disks are designed to work. So that's great. We've kind of solved the big problem. We can grab a specific page off the disk. But, we've just created a miniature version of the exact same problem. A page is still just a jumble of records. How do we find the one we want inside that page without scanning it from start to finish? And the solution to this puzzle is a truly elegant piece of engineering. It's something called the slotted page layout. Okay, picture this. At the very start of the page, you have a little directory. It's just a list of pointers. Then, the actual data records, they get added from the end of the page, growing backward. So you've got the pointers growing from the front, the data growing from the back, and they both head towards the empty space in the middle. Pretty cool, right? And here is the absolute key insight, the genius of this whole idea. The actual data can be a total mess. It can get added in any random order. But that little directory of pointers up front, that is always meticulously kept sorted by the record's key. We're creating order in the small, easy-to-manage pointers, not in the big, clunky data itself. Now, because those pointers are sorted, we can unleash a computer science superpower, binary search. Instead of a slow one-by-one scan, we jump straight to the middle of the pointer list. Is our target key higher or lower? Okay, great. We just throw away half the list in one go. We do it again on what's left, and again. In just a handful of jumps, we found the exact pointer to our data. It is unbelievably fast. Okay, so we're masters of finding a record inside a page now, but a real-world system has millions, maybe even billions of pages. How in the world do we find the one correct page to even start looking in? For that, we need an index. You can think of it as the master card catalog for the entire dataset. It's a whole separate structure, and its only job is to take the key you're looking for and tell you, hey, go to page number 8,675,309. It lets us completely skip over all the millions of other pages and go directly to the right one. Now, there are basically two main strategies for how to set this up. You can have an index file that's totally separate from the data files. It just stores pointers. Or you can use what's called an index organized table, where you actually store the data records right there, inside the index structure itself. So why on earth would you put the data inside the index? One word: performance. Every time the system has to jump between files, like from the index file over to the data file, that's called a disk seek. It's a physical action that takes precious time. By putting the data right in the index, once you've found the key, you've also found the data. No extra jump needed. You save a trip. All right, let's put all these pieces together now. We're going to trace a single query from start to finish just to see this whole beautiful, orderly system in action. So it all kicks off with a simple request. Find a record with this specific key. The system's first move, it goes straight to the master index, and it just flies through the structure to zero in on the right entry.
That index entry gives us the treasure we're looking for, the exact address of the single page on disk that holds our record.
Now we're at the micro level. The system grabs that one page from the disk and then unleashes that lightning-fast binary search on its sorted pointers. And just like that, there it is. The record is found. In a few highly optimized, incredibly efficient steps, we've gone from a chaotic sea of billions of bytes to the one specific record we needed. From chaos to order. This is the blueprint that makes modern data systems possible. So we've built this incredible blueprint for finding data with amazing speed. But this very system for order and efficiency creates its own fascinating new challenge. What happens when it's not just one person looking for data, but thousands of users, all trying to read and change things at the exact same time?